Welcome back to another explainer. Today, we're diving straight into the sheer architecture of life itself. Just think about the staggering variety of life on Earth, from a highly complex mammal navigating the forest floor to a delicate jellyfish just drifting through the deep ocean. Almost every single creature you can think of shares a massive hidden rule of design. But then, there's the sponge. Today, we're unraveling the absolute mystery of animal symmetry. We're going to explore why virtually everything on Earth is perfectly mirrored, exactly how it biologically happens, and why the strange, lopsided exceptions to this rule are so incredibly fascinating.
So, what makes the lumpy sea sponge the ultimate 1% rebel? Well, picture a sponge out on a coral reef right now. And no, obviously not a discarded kitchen sponge, but a living, breathing animal. It has no head, no tail, no front, no back, and literally no left or right. It's essentially just a lumpy blob of cells sucking in seawater and filtering out food. If you were to slice almost any sponge down the middle in absolutely any direction, there is no way the two halves would ever match up. And yet this totally shapeless, asymmetrical existence, it has worked gloriously for nearly 1 billion years.
Okay, let's dive into this. Here is our evolutionary detective journey for today. 1. The asymmetrical sponge. 2. Bilateral and radial body plans. 3. How embryos build a mirror. 4. Why movement creates symmetry. 5. The lopsided animal revels. And finally, 6. Are we truly symmetrical?
Section 1. The asymmetrical sponge.
Now, you might be wondering, if the sea sponge proves that being a shapeless blob with absolutely zero aesthetic sense is a perfectly legitimate way to survive, why doesn't everything look like that? That's what makes the sponge's success so wonderfully strange. Think of literally any other animal, a dog, a shark, a tiny beetle, a bird, or even yourself when you look in the mirror. You draw a line down the middle, and the two halves mirror each other almost beat for beat. Despite the sponge proving for 1 billion years that symmetry is entirely optional, over 99% of all animal species went ahead and locked themselves into a mirrored layout anyway.
Section 2. Bilateral and radial body plans.
To really get why 99% of life looks the way it does, we need to nail down this core concept of animal symmetry. Basically, this is the fundamental layout of an organism's body plan. It categorizes exactly how an animal's parts align across spatial axes. Now, we've talked about asymmetrical bodies, where there's just no matching alignment at all. But for that remaining 99% of life, they mostly fall into two main camps, radial or bilateral. And honestly, grasping the difference between these two is absolutely crucial for understanding how life operates on Earth.
So, on one hand, we have radial symmetry. Think of a floating jellyfish. It meets the world from all directions at once and is perfectly content just drifting around. It has a top and a bottom, sure, but no distinct left, right, front, or back. But on the other hand, we have bilateral symmetry. This layout is built for directed locomotion, animals that are purposefully moving in one specific direction. Because of that constant forward movement, they develop a clear front, a back, a left, and a right. But here's the catch. Getting to that clean bilateral setup is actually incredibly tricky for biology to pull off.
Section 3. How embryos build a mirror.
We know what these body plans are, but how does a tiny, blob-like embryo actually know its left from its right? I mean, building a mirrored body isn't just some magic default, it's this massive, highly coordinated biological construction project. Check this out. In step 1, Hox genes kick off super early, essentially shouting orders to assign the front-to-back axis. They literally dictate, okay, this is the head and this is the tail. But how do they find left and right? Well, step 2 is just fascinating. Patches of tiny, hair-like structures called cilia tilt back and literally spin. This spinning drags fluid across the embryo in one steady direction. That microscopic physical current is the ultimate tiebreaker. Then, step 3. Whichever way that little current sweeps triggers nodal signaling, which specifically switches on the PITS2 gene strictly on the left side. That is exactly how the embryo intentionally breaks its own blobby symmetry to assign a true left side, all while somehow maintaining a flawless outer mirror. It's wild.
And we know exactly how crucial those little spinning cilia are because of what happens when they break. In lab studies, mice engineered to lose those cilia actually have their left and right completely randomized. In humans, broken cilia can lead to a really rare condition called situs inversus. This is a condition where your internal organs develop as a flawless mirror image of the normal setup, so your heart is shoved over to the right and your entire gastrointestinal system flips. But the amazing thing here is that the body doesn't just melt into chaotic asymmetry like a sponge. No, it builds a perfect mirrored copy of the normal arrangement. Literally every organ is in the wrong spot, but they are perfectly in the exact right wrong spot.
Section 4. Why movement creates symmetry.
So, we've seen how the body physically pulls this off, but why symmetry at all? Why go through all that intense genetic trouble? Well, the crucial point is summarized perfectly in this quote. Symmetry is really just a consequence you get the second something becomes a thing that wants to move. Let's really break that down. Our planet hands you your first access through gravity, right? Up is permanently different from down, so it makes total sense to build a distinct top and bottom. Then, the very moment you decide to start moving in a specific direction, the end of you that goes first naturally runs into all the food and all the threats, so evolution highly favors cramming all your senses and nerves up there, creating a head and giving you a clear front and back. But what about left and right? Well, as far as the environment is concerned, your left side and your right side are dealing with the exact same world. There is zero evolutionary reason to build them differently. So they just come out the same by default. A mirrored body is really just the elegant leftover consequence of moving through a 3D world. Plus, biologically speaking, it's incredibly cheap. You write the genetic code for one half and just copy and paste it for the other.
And the cool thing is, we can actually track this exact progression in the evolutionary timeline. A billion years ago, sponges were doing great just sitting there as asymmetrical blobs. But jump to about 555 million years ago, and we find this tiny creature called Icaria wariotea. This little pioneer was actively shoving its way through the ocean mud. It had a genuine front, a back, and a beautifully mirrored left and right. This fossil basically pinpoints the exact moment when directional movement and bilateral symmetry officially teamed up. Fast forward to the present day, and because that highly maneuverable, mirrored design is just so ridiculously successful for hunting and surviving, over 99% of all animal species rely on it today.
Section 5. The Lopsided Animal Rebels.
So, since a mirrored body is genetically cheap and the super easy default for moving creatures, overriding that symmetry to be lopsided on purpose actually costs a ton of energy and evolutionary effort. Yet, some absolute rebels in the animal kingdom decided to break the mirror anyway. First up, the flatfish. It actually hatches perfectly symmetrical, but during its growth, one eye literally migrates across its skull to the other side. This allows the fish to flop onto its side and basically cosplay as a scaled rug on the seafloor. Then you have the fiddler crab, just lugging around one massively oversized fighting claw while the other stays tiny. And the majestic narwhal? No way. That famous unicorn tusk isn't a horn at all. It's specifically their left tooth, drilling straight down through its lip. What's truly fascinating is that when you trace these lopsided animals back up their family trees, their asymmetry is almost always a much newer invention, just slapped onto ancestors that used to be perfectly symmetrical.
Section 6. Are we truly symmetrical?
Now, what's really interesting about this is, well, before you get too smug about being a perfectly balanced, aesthetically pleasing human, let's take a closer look at ourselves, because it completely shatters the illusion of perfection. Your outside might be a nice, tidy mirror, but inside, you are a lopsided mess. Your heart leans distinctly off to the left, your liver camps out entirely on the right side, your gut is coiled in a very specific asymmetrical direction. Sure, biologically, you are classed as bilaterally symmetrical because of your overall body plan and the way you move, but internally, you're a little crooked too. The perfect mirror is really only skin deep. So, wrapping all this up leads us to a massive, literally universe-sized thought. Given that symmetry is essentially a mathematically elegant response to the physical forces of our world, specifically gravity giving us a top and bottom and directional movement giving us a front and back, would extraterrestrial life be bilaterally symmetrical too? Because those axes of physics are universal constraints, it is highly likely that if we ever do meet aliens, they won't just be random floating blobs. They might actually be mirrored right down the middle, exactly like us. Though I gotta say, they probably won't look exactly like Clark Kent. What an incredible journey through the architecture of life. Thank you so much for joining me on this explainer. If you enjoyed diving into the weird world of ancient sponges, migrating flatfish eyes, and the underlying physics of symmetry, make sure to hit that like button, subscribe, and leave a comment below. I really want to hear from you. What is your absolute favorite animal layout? Are you team bilateral, team radial, or are you joining the 1% rebel sponges? Let's get the discussion going in the comments. See you next time.